Hello from NASA's Ames Research Center. My name is Brian Day and I am the Education and Public Outreach Lead for NASA's Lcross Lunar Impactor mission, the mission that is going to the moon to study potential deposits of water ice there. We have Dr. Peter Schultz with us today from Brown University. Dr. Schultz does a lot of research here at NASA Ames Research Center using the vertical gun range. Pete, can you tell us a little bit about this research tool?
Yeah, the NASA Ames vertical gun is a very unique facility. It's 3 stories high when it's in the vertical position, but it can go in different angles, which is critical because impacts come from all directions.
So what does the vertical gun look like and how does it work?
The gun actually is a very long launch tube attached to a yoke that goes up and down depending on the impact angle. But the business end, that is where the impact occurs, is in this large chamber. We actually walk into the chamber and we can prepare the targets. That's what really makes this gun quite unique.
Now this particular research tool has been in use for some time, hasn't it?
The gun was actually created in the mid-60s, and it was initially used just to understand what the surface of the moon would be like. And since then it's been used to help define what we find on other planets, from Mercury to Mars to Venus. And the outer satellites of the Jovian planets. It has been in almost continuous use since the mid-60s. It goes all the way back to prior to Apollo. It was used to help define what the nature of the surface was going to be as we were prepared to land during the Apollo missions.
Now today you're using it in support of the Lcross mission. How are you doing that?
The gun is perfectly suited to investigate what's going to happen during Lcross. So the types of experiments we've been doing are twofold. One is to see the flash. How bright will that flash be? And that helps us, give us an idea of what might happen during the impact event. The second is to watch the debris that's thrown out of the crater. That is the ejecta. This is the stuff that will come up, be illuminated by the sun, and allows us hopefully to see if there are volatiles buried beneath the surface. So we do experiments to kind of visualize what we see, but more importantly, to actually understand how much mass gets thrown out, from what depth, and if we see any evidence of volatiles, where are they coming from?
So you mentioned that this is going to help us locate volatiles in the plume. Just what do you mean by the volatiles?
By volatiles, what our best wish is that the volatiles will be water. Volatiles can be anything that easily evaporates. So it could be CO2, it could even be hydrocarbons. But all we know is that there's an indication of hydrogen coming from this region in the permanent shadows of the poles. And the first assumption is that that hydrogen is coming from water. So we don't know specifically what it is, but we suspect it's water. And if so, when we dig down and excavate, bring it from below and toss it into the vacuum of space, we'll be able to tell by the instruments on board Lcross.
So based on your research, what do you anticipate the plume is going to be like? How much material will we excavate? How big will it be? How long will it last?
Well, we expect, if everything goes right, that the crater will be something on the order of 50 feet across, which is pretty big. And it may go down to maybe 6 feet deep. The amount of material that will be tossed up will then form this cone. It'll look almost like a funnel. They'll extend down to the surface. But what we'll see, that is from the Lcross instruments, will be a ring of debris that will then get larger and larger with time and fade as the crater finishes forming. The crater will finish in less than a second, but the crater ejecta, the debris coming off the surface, will continue to expand as they are comprised of these ballistic trajectories of the debris coming off the surface of the moon. In addition, there will very likely be a central plume, that is a cloud-like area that will come in the center. So we may see multiple components. But the reason we do the experiments is to find out what happens if it doesn't look quite right, and what happens, can we tell instantly if we see something really exciting, what really went on, what happened.
Are you able to make any kind of estimate as to what people here on the Earth may be able to see of this plume?
I think of what we'll see from the Earth as if you're sitting in the middle of a cloud. You know, you see the haze, but you really don't see the detail. But when you see it from a distance, you actually see a form, a shape of the cloud. That's the same thing for Lcross. We're close up with the Lcross instrument. It will look like a ring of debris, but from a distance from the Earth, it will be more like a haze that will extend above the surface of the limb of the moon right after impact.
We are finding that there's great interest among students and amateur astronomers in observing and even imaging this impact plume that we create. How could those images be useful to researchers like you and to NASA?
I wish I were looking at it with a telescope. I mean, I'm an amateur astronomer at heart. I was ever since I was a kid. I would love to see it in my backyard, but it's going to be really interesting because if there's any problems with the instruments, or because we are looking at it from a distance, it's going to be, all these particles are going to be looking much more packed together when they emerge above the surface. And it may be that it's going to be more easily seen by observers from the Earth than that very close-up picture from Lcross. So it's going to be critical to get these images from telescopes on Earth, and especially having amateurs involved, because a bunch of set of eyes is always better than just one.